Welcome to today's AIM Academy webinar, part of our ongoing series designed to make cutting-edge material science and engineering knowledge more accessible. My name is Zara and I'll be your host for this session. Today's talk is on the digital factory, AI, digital twins, and the future of materials manufacturing, hosted by Dr. Alexei Lapkin, Chief Strategy Officer at Accelerated Materials. And in this session, Alexei will explore the foundations of digital infrastructure for R&D and manufacturing, and why connected data systems are becoming critical for modern materials development. How AM Learn supports data-driven experimentation and forms a key component of a broader digital innovation ecosystem. An introduction to digital twins and their role in accelerating process understanding, optimization, and scale-up. How ontologies and structured data frameworks enable interoperability, knowledge capture, and smarter decision-making. We'll also have a look at how Accelerated Materials is developing a digital twin of its manufacturing platform to support future autonomous operations and continuous improvement. We'll also leave time at the end for a Q&A, so feel free to drop your questions into the Q&A box throughout the session. And with that, I'll hand over to Alexei to begin.
Thank you, Zara. I'll begin. So we'll talk about manufacturing, and to begin with, I will start with an abstraction. So why do we manufacture things? We manufacture products, whether those are molecules or materials, to deliver useful functions. Those useful functions are defined by customers, and the delivery of these useful functions can, of course, vary. So it's not necessarily that you need to produce a particular material, you need to deliver a function. Now we're talking about chemistry. We are delivering functions with specific products. Those needs to be produced, and the manufacturing is the conversion of raw materials through a value chain to the final products. And of course, there is always some harmful functions. Those could be emissions, those could be fate and the end of life, or just cost of recovery and so on. In the manufacture, you necessarily spend some energy in every step, and you necessarily will have some wastes. So that's kind of the overall picture of manufacturing. And in recent years, the design vector, the set of target properties for manufacture has significantly expanded. So this is a typical statement from a customer of what do they want to have. For example, they want to make a new material with a particular property X, whatever that is. They want to make sure that there is no patent infringement. If this material goes into the end of life in the environment, it needs to be biodegradable, it needs to be non-toxic, easily manufacturable, having a low-cost starting material. Those materials should have a low environmental impact, and the overall process should be cost-effective. This is a 7-dimensional design vector, which is really, really difficult to hit. And so the way how we design materials these days, the way how we manufacture them is rapidly changing because of the need to hit a significantly more complex design specification for materials and molecules. We do manufacture in the systems. The manufacturing plants are collections of unit operations. They are in specific order. They interact. And so what we have as a manufacturing process is a complex systems. Because this is a complex system, those are quite difficult to create. And the degrees of freedom in the final manufacturing process are relatively few. What we note that the final optimal, globally optimal way of manufacturing a process is usually a sequence of suboptimal units. If we optimize each step individually and put them together, that doesn't work. We really have to optimize the whole system together. And now, as we have this wider design vector for materials, our global optimization is now even bigger than just the operation. we also need to take into account the environmental impacts, the supply chain, and so on and so on. So this really is becoming harder. And just to show you the last slide, which shows that this is difficult, is the scale and the dynamics of the process. So if we're looking just at the manufacture, we have a process. Process is a collection of units. Let's say we have a reactor underneath that. Within the reactor, we'll have certain phases. Within that, we have each phase consists of molecules and consists of atoms. So we have this hierarchy of scale, and then it's also in time. So we go from the starting materials, which are placed into the plant, go into the products. The products are typically either materials, so phases, combination of phases, or a combination of phases and molecules. And then these are the products, and then in the use phase, we have this combination. So it's quite a large collection of different scales. And in order to cover the science of this, we cover a lot of different disciplines. So technically, this is not an easy task to put this together. So now we're talking about process design using new tools and then process manufacturing using emerging tools. So what we're trying to do is combining the knowledge about unit operations. So what do we know about this? What are the tasks? What's inside? What are the conditions? What's the physics and chemistry inside? To create a first principle model. The first principle models is our summary of our understanding of what's going on. It may be slightly wrong, it may be simplified, but that's what we understand about what's there. It's a research tool, and the first principle models are also used in optimization and control. We can collect the operational data from the running of the plant, and then that gives us the statistical models, which can be used also in control and optimization. It also can lead to tasks such as anomaly detection, fault detection, and so on and so on. And then if we combine the first principle models and the link to the operational data through sensors and the feedback to the actuators in the plant, then we have our digital twin. And so in this case, we can start talking about digital laboratories, digital factories, tasks such as real-time optimization, predictive maintenance, anomaly detection, and etc. So I'll show you how we build these things and how the technology evolves and what's underneath, under the hood in developing this type of technologies. I'm going to anchor this on accelerated materials technology. This has been developed over many years. There's multiple scientific publications on the technology itself. So we have quite a bit of fundamental understanding how this works. And so we can build physical models. We have the sort of a Mickey Mouse pictures of how the technology, what the reactors look like. We then have technical diagrams. Again, they're not very specific about what's going on. We can start picturing the phenomena which is in this process. And then we have the actual plants from which we can collect the data. So there's a lab plant with sensors, which we then can use to collect the information. So in process development, we're trying to optimize the product. So in this case, if we are making zinc oxide, we need a particular type of crystals to perform specific function. We are creating these loops for optimizing the operating parameters, which is the concentrations, the flow rates, then to have the specific properties. You can do it manually, but you can also put this into a closed loop optimization system. So the closed loop optimization systems these days are very popular. You have an experiment which is either manual or fully automated, where you need to automate not only the experiment itself, but also the analysis of the outcome. So whether this is a crystal structure, whether this is some other property. And then you have an intelligent algorithm, typically Bayesian optimization is being used here to design the next one or a sequence of experiments to perform. And if this is fully automated, then you can run it as a closed loop and you don't need human intervention. It could be partially automated as well when the human operators can enter the data of the analysis into the system to then run the next experiments. Accelerated Materials have created a product for this. It's called AM-Learn. So this allows to automate third-party equipment and run Bayesian optimization if you want to have a look at this version of Bayesian optimization. So let's say we are optimizing the zinc oxide for its microbial activity. And in this case, our analysis is the disk test with microbial cultures. And looking at this result, we feed them back into the algorithm and then optimize the conditions. We run this campaign. It's run as an active learning loop. So there is an algorithm here, which is called TSIMO. The current version of AM-Learn has a more advanced algorithm than this, which then suggests the new experiments. The advantage of doing process optimization with this kind of systems is typically the amount of effort, the reduction in amount of effort you need to do. So this is a comparison of achieving the results with this TSIMO algorithm compared to classical factorial designs, and the TSIMO allows to reduce the experimental effort. If you do it without experimental design, this is even better compared to the manual operations. So in the lab scale, the use of the digital tools, when you have an equipment which is automated with the machine learning codes, allows to speed up the development of the products. So this is the statistical model. So we collect the operational data, analytical data, and develop a statistical model. So now that's not enough to build a digital twin. We prefer to also have a first principle model, and you will see later why we want to do that. So here's our problem statement. We would like to have a first principle based models, but the model development is quite a difficult task. It requires a very high level of expertise. You need pretty much three people. You need a subject matter expert who knows the science of the problem. You need somebody who really knows how to use the tools for design. Typically, people use commercial tools. And you need somebody who really knows the modeling problem itself, because identifying the model calibration is not a trivial task. So this is sort of a three-man job. There are very good individuals who can do the whole lot themselves, but typically this is more than one person. So we're asking the question, is it possible to automate model development, making use of the existing knowledge of science and engineering, which is domain knowledge, existing knowledge of process systems engineering, which is how to correctly identify, calibrate, model, and design of experiments, with reasoning capabilities of AI. So this is then another application of artificial intelligence. So what we are ultimately building is the connection between our experiments, whether this is a lab scale. Initially, it's a lab scale, and then later I'll show you also the plant. With the knowledge base, we're going to use the technology called knowledge graphs and explain why, where we expose the process data, the physical models, and the AI models in the agentic way, so that we can do things like simulating the process, identifying the model, calibrating the model, and optimizing the processes. So that's our target. Now, in order to develop this, we chose the technology called knowledge graphs. And the knowledge graphs allows us to achieve three simultaneous tasks. Expressivity, so everything is semantically annotated, so we know what's going on. All the models are highly interpretable. Everything is standardized, which means that we can use multiple tools, multiple different vendors can access the same technology and so on. And interoperability, which means that we can connect multiple domains, whether this is making materials or making molecules, analytical technology, different types of plants, different types of manufacturing. These are technologies or the sectors which can all use the same underlying core technology if they are using the technology of knowledge graphs. Now, in order to do that, we have to introduce the language of the modeling and the language of communication within the knowledge graph. And that language is based on the concept of ontologies. Ontologies is an ancient concept. This comes from philosophy. It's also the foundation of computer science. Without ontologies, computer science, the way we have it today, and the AI would not be able to exist. Ontologies is a way of creating a consensus of the representation of knowledge. And that allows to share information across software systems, share information across technical systems, and so on. Within the ontologies, we define the language. How do we communicate? How the instruments communicate? What do we know about our systems? So we define things like classes. So what are the entities? What exists in our universe, in our understanding of systems? We define specific entities, the instances of members of the class, their relationship. This is the most important bit, how things relate to each other, as well as ground truths, some propositions that are always true, which allows us to calibrate against the most foundational statements. Now, ontologies have been in development for chemical processes for quite a while. We have a very large ontology. This is published in 2009. This is called OntoCape. It is a complicated picture. It is a humongous ontology. It covers pretty much everything in chemical processes. When we develop ontology, we typically start from this. And then when we see that something is missing, we extend and link with existing other ontologies. So how does it link to chemical processes, and how this links to the technology of developing models? So what we've developed recently is an extension of the process ontologies when we have an ontology of the model. An ontology of the model describes what a model should have. A model has a certain physical law. These laws have variables within them. The variables have symbols and units and dimensions. The laws has a formula, the final way how this law is expressed in mathematical language. Sometimes they have a reference. So if the law was developed by a particular person and you have an equation published, then there is a reference to that publication. Then these laws correspond to specific physical and chemical phenomena. So what we do in this ontology, we quantize the complex expressions or the complex physical laws into the underlying phenomena. And so some of the laws are very simple. Newtonian law, each one of Newtonian laws is a single phenomena, but some may be more complex. You can have mixing together with heat transfer, you can have a reaction together with mixing, but we just describe them separately so that we can recombine this phenomena in different ways. So this is the first ontology, which is ontology of the models. We then also link it to the process ontology. So there are certain rules how the laws are combined together, how certain phenomena can be combined together. This is linked to the units operations of the plant. So whether this is a reactor or a separator and so on. And then these allows us to connect to the query language. So you can have a query which then talks to the knowledge graph and assembles the information. So when we're creating the system, we're using the MathML language to express the models. And this is very useful because MathML can be expressed in HTML. So our web page shows the equations in the way scientists can understand, but also those are parsable. So we can express then the models as the Python code or Pyomo or Julia, so different languages to run the model. So what does this allows us to do? If we take the case of assembling a model, we have a different types of phenomena. For example, here is a heterogeneous catalyst, which also has a photocatalysis. So there is already complex phenomena. Those phenomena exist in the knowledge graph. And if they are selected by the user, the system will assemble the equation which contains the description of both the photochemistry, this first part, and the Langmuir-Hinckley-Wood kinetics, which is the second part. The expression says the user selected that they have an ideal plug flow. That means that the expression for the mixing terms are specific. That means that there is no dispersion in the system. So some of the terms which go into the final equation of mass accumulation are then zeroed. And so the final equation for mass accumulation, which is then a physical model, is assembled from the underlying phenomena which are selected by the user. Sometimes the users don't know what exists in the process. So they have the data, but the technology is quite complex, and the user may not necessarily know exactly what phenomena to choose. So in this case, we use a technology of process context, which is the six-dimensional descriptor, looking at structure, space, energy, substrates, information, and time, to assemble plausible models for a specific system, and then do the process which is called model identification. So which of those assembled models are most likely to correctly represent the physics of the process or the data which is assembled. So for the case of accelerated materials reactor, the same reactor I've shown you before, the model will assemble what's the flow pattern, what's the mechanism for molecular transport. We're using this reaction, which is a standard reaction, to characterize mixing behavior. It's a very fast chemistry. Depending on the type of mixing, you will have different concentration profiles. So it's a very good indicator of whether you have micromixing or not. Then this assembles into the final concentration derivative, and that allows us to simulate the reactor and also to calibrate it. So this is effectively an assembly of a first principles model, which can later be calibrated against specific unit, which gives you a digital twin for that unit. In the case when we don't know the model, we did it for a different reactor. This is a Taylor-Couillette reactor. When the nature of the model changes depending on the operation of the reactor. So here the central disk cylinder is rotating, the wall is static, and the mixing behavior depends on the combination, on the interplay between the rotation of the cylinder and the rheology of the fluid. And so if you change your operating conditions, you may go from one type of model to another. So here we assemble all possible models. So there is a multiple models which could coexist, and then calibrate all of them. And we see that in specific conditions, different types of models are correct. And so that allows us to then see, okay, you actually need to go from one version, one model to another model in your digital twin. So this technology has been developed to the point when we've transitioned this work from academia, from my research group at Cambridge, into another of our startup companies called Chemical Data Intelligence. This is now a product. It's going to go on the market in the next few months. When the knowledge graph is available, the users can assemble the model. This is a window from the model exploration when the equations are shown. This is for the case of fed batch hydrogenation chemistry. This is an illustration of the same version for the accelerated materials reactor with this mixing experiment. So now, okay, we have a first part of the digital twin. We actually, I already talked about two parts of the digital twin. We can assemble statistical models through active learning loops from operational data. We can also now assemble physical models using this knowledge graph technology. So now we're trying to create a full digital twin. And in this case, what we're trying to do is to take data from a pilot plant, in this case, the accelerated materials pilot plant, and link it in the full architecture for a digital twin. So we combine the physical model of the plant, of the part of the plant, with the statistical data, the model built on the data coming from the plant, and we're putting it into the overall architecture. We did this for a subset of the plant, and we were demonstrating this in the public project with accelerated materials giving us access to some of the data from the plant. So what did we want to illustrate and how this overall architecture works? So I'm going to spend a bit of time on this slide. So we have a plant. There is a physical device. A physical device, of course, requires certain security. So we need to make sure that there's no possibility of hacking the signal if the plant is running and we are collecting real-time data from it, sending it to the cloud environment or edge servers where intelligence is being collected. So here we might have historical data sitting on the plant in the local servers. We have a test server here. Then we have an edge virtual machine. This is a server which was running by the institute. I2R is the A-Star Institute in Singapore. It's now called differently because it's just merged with another institute, but a few years ago it was I2R. Here there is data processing, and the data is enhanced. Kind of the raw data is semantically enriched and sent into the correct data storage. The data storage is on the cloud. We use the Microsoft platform Azure. And in this case, we have two types of data storage. There is actually more than two. There is a MongoDB, the database for tabular data. You may have very large run data when you have time series for experiments, or you may have images, or you may have other types of data. Those are heavy files. You typically need to store them in the cheapest possible store. And sometimes you don't need to keep this data for long, easily accessible. Then you move it into the cold storage. So this is the tabular data. Then you have some relational data. in the Postgres database. And then you have the knowledge graph with the ontologies, and that sits in the graph database. So this allows us to store different types of data and connect or create the accessibility of the data by the agents, as well as the environment where we can place new agents into this architecture. So here we have a bunch of agents which we've constructed. So there is the assembly, so anomaly detection agent. There is a physical model for anomaly detection. There is an agent which works with the time series data. There is the agent which generates the ontology itself. There is the agent which works with metadata. There is a post-processing agent and so on. So these agents all work with this data architecture which is created. And then you have a user interface. So the user interface is then connected to this overall infrastructure. So this all together creates the full digital architecture for a digital twin. This is completely scalable. You can build one of those for the lab. You can build one of these for the plant. It solves quite a lot of problems for the security of digital communications, making sure that the plant is not hackable in operation, making sure that the data is secure, the users cannot do something stupid whilst the plant is running, and so on and so on. So within this, we have quite a lot of agents which are required to work with this architecture. So this is a little bit more detailed diagram of how the agents are connected, what's going on, how the data is being flown. So from the test servers or from the real plant or from the simulated data, where which agents work with the raw data, process it, create the time series and relational databases. Which agents then here are the model agents. We used the problem statement of how to identify if the plant is operating incorrectly. So this is anomaly detection. The GraphDB contains the information about which data is what are the different parts of the plant, what are the different models, how they all interact with each other so that the agents can assemble the right information to work. And those three are then working with the users through the REST API. For the anomaly detection, we have created a specific workflow when we asked how best to make use of both the availability of the raw data coming from the plant and availability of the physical model. So effectively, we are having two parallel models running together, or you can run them separately. The physical model is what you believe the plant should be able to do. It doesn't have the connection to the actual sensors, but it's calibrated on the plant data. So it should give you a reasonably good description of what you should expect when you're running the plant. Whereas the data-driven model has access to the historical data as well as the real-time data. So what you can do is you can run both of those together, and you can see when the plant deviates from the predictions of the physical model, when the plant deviates from the prediction of the statistical model. And then gives you an indication that you do have a fault in the plant. For the anomaly detection, the the physical model, I think I have a more detailed slide of this. Also, the statistical model was built on the autoencoder architecture. So you normalize the data, you train the model, you compute the error, then you detect the operational stage, you identify what are the most erroneous parameters. If the errors are exceeding the threshold, then you have a decision making what to do, whether this is a normal operation or whether this is a flag which is given to the user. The physical model is you have the data, you query the ontology, you configure the model, you calculate the errors with the configured model, and then you see, okay, are you exceeding the threshold or not? So again, this works with the specific data architecture. So it makes sense to just show you a little bit more detail here. The graph data is the ontology. So here is we've created a scripts which allow to convert the ontology with the new incoming data into the graph database. So this is fully automated. The time series data is the sensor data from the plant, and that is going through a script, then goes into a database, and the database is then allows to look up specific elements of data which are required for specific agents to use later on. The autoencoder model is very popular. You probably, if you are into machine learning, you've seen this. There are two neural networks. There is an encoder network and the decoder network. You are training the low dimensional latent space to represent what's going on in your plant. In our case, what we want to understand is whether the error of operation of the plant over a specific operational window exceeding the threshold. So here we are measuring 5 times within 20 seconds. If the error exceeds a particular threshold within that window overall, then there is a flag. Why are we doing this? Sometimes there are spikes on the sensors, sometimes there is just electric signal going through. And so if it's a spike, we don't need to act. But if it's repeated, then it probably is an error. So this is how it's represented here. If it's just a spike, it's not a problem. But sometimes if the threshold is exceeded for longer, then yes, we then need to act. So in the actual plant, which I can't show you because this is the real plant, so quite a lot of it is blocked out, we see in operation that a lot of the times this is normal operation. The users basically see the board. It says, yes, it was normal, normal, normal. But in some cases, we see the fault detection. We were simulating this with the plant, creating specific cases when there is an anomaly, basically deliberately making something wrong on the plant to collect the data and seeing whether the model actually is able to identify that there is a problem in the plant. So I've been describing this very quickly, but hopefully this will give us time for questions. What we were trying to do in this project is to show the advantages of building digital twins on knowledge graphs and ontologies. You can build digital twin without a knowledge graph, but it will be highly specific to a plant and to the equipment which is being used. And that technology of digital twins is not scalable. You have to then rebuild it every time for slightly different versions of the plant. If you have a knowledge graph, the generic knowledge of the types of equipment which is in operation in a specific organization is already in the knowledge graph. And so recalibrating, slightly changing the models is an embedded feature of a knowledge graph. And so this becomes much, much more scalable. So the knowledge graph gives you semantic understanding and interoperability of what's going on. What are the relationship between your physical assets, your sensors, your metadata, what was done, how it was done, why it was done, and the actual observed events. This allows the cross-domain knowledge sharing, and it allows a in-depth understanding of the technologies. Sometimes for organizations, just having a knowledge graph and an ontology of the process significantly enhances the ability to operate. This enhances the knowledge of the plants, and the significant value for the organization is held in that knowledge graph itself. Then if you are linking this with the agentic framework, in this case, you have a lot of flexibility. The agents are being designed all the time. The new machine learning architectures are appearing. The new concepts are appearing. The generic foundation of knowledge graphs allows to drop in new agents, replace the older agents, and perform better and better tasks. Sometimes organizations don't even know what they want to do with the digital infrastructure. And as they see the evolution of the data, the evolution of the knowledge, which comes in from digitizing the plant, the new use cases appear. So here we shown that we can improve the anomaly detection by understanding the context within the anomaly. So the context is basically, we can very quickly pinpoint what has happened on the plant because we have relational knowledge about the different units in the plant. So whether this is a sensor fault, or whether this is a valve fault, or whether this is an operator error, the idea of what has happened, what's gone wrong, is very quickly detected because the relationship between all of the units in the plant are already described and already exists in the plant. Then this helps with the decision making and gives an insight into the operations. This architecture is completely scalable. We can build modular virtual machines and the agents and create this very rapidly for hundreds of units of operations connected into larger systems. And this also allows to use efficient data management. So you can have expensive storage, such as relational storage, only restricted to relatively light ontologies and knowledge graphs, whereas your tabular data, the heavy data, such as tables of raw data, images, and so on, stored in a much cheaper storage. So what I was describing you was a project which was funded by Pharma Innovation Program Singapore. It was a collaboration between the University of Cambridge, our academic team in Cambridge Center for Advanced Research and Education in Singapore. We also involved the A*STAR Institute, I²R, which has just merged with another institute. It has a different name now, and with the team from Accelerated Materials. What we've learned, we've built the foundation for digital twins technology based on knowledge graph. Part of it, the model development tools, is now a new software product, which is going to the market soon. We've demonstrated this on a pilot plant of Accelerated Materials as our digital factory. And we see that there will be a wider development in this because the agentic framework is something which is definitely coming to both R&D and manufacturing. Agentic framework requires the safeguard of the knowledge graphs and ontologies. Without these, agentic environments basically don't work correctly. So this is not something which could be avoided, in our opinion. It's something which is absolutely necessary. So this was our academic team. The information about how to build ontologies of the digital plant, of the actual plants, and how to create secure data communication was done by the group of Marcus Kraft. The demonstration, the full implementation in Azure was done in A Star by the group of Lilian Zhang, and the model development, the model and process ontologies. So the theoretical foundation was done by my group in Cambridge and in Cairns. So with this, I'll finish.
Thank you, Alexei, for that insightful session. We have a few questions, so I'll just zip through some of those. Do we need professionals with AI agent skills to operate or use this digital twin, or can it be trained to existing manpower with domain skills?
Well, in order to operate, you don't need to have AI trained people, because these days the expectation is that you have an intelligent chatbot which interprets the users or the operator's instructions and communicates with the agentic system. So one of the agents is the interpretation agent. People are getting used to talking to ChatGPT or to Gemini or to Claude. In many cases, you can have one of those agents as your front end talking to the users. So you don't need an expert. You have an interpreter of the natural language into the rigorously correct instructions, which are then understood by the AI system.
Thank you. Many organizations are still working with disconnected data systems. What do you think is the biggest barrier preventing companies from building truly digital R&D environments?
Sometimes it's the lack of internal skills. Sometimes it's a lack of resources. Sometimes it's fear of the loss of data. It depends. There is this sort of hierarchy of digital readiness. And if the company is at the digital readiness 0, then of course this is an incredible risk, and it's very, very difficult for companies to progress. They need to have a digital readiness plan. They need to understand what's involved, but mostly they need to understand the potential value, either in increasing the operation efficiency or being able to bring products to market faster, or there is inherent value in the data they have. So there are multiple types of value which organizations might have. And understanding of that is critical. If companies don't understand this, they're probably going to go out of business because their competitors will do this. And that for some people, this is, or for some organizations, this is existential risk.
And what is the value proposition demonstrated based pilot testing that you mentioned?
So here is a very specific use case when a plant has a continuous operation, and the if there is a fault in the this was done particularly on the feeding module of the plant. If there is a fault there, that needs to be detected very quickly. Otherwise, it continuously damages the product which is being manufactured. So the faster you detect that fault, the quicker you can remedy. So this is basically loss of revenue and operational efficiency of a plant.
So at what point does a process become mature enough to justify building a digital twin?
Well, actually, this is a very good question because you could do it at different steps. So what is possible, and there are colleagues of mine who work on the using the digital tools to gradually develop the process. So you can even have a fairly new lab scale process, which is not scaled, and start co-developing technology and the digital twin of it, because the two things help each other. The more work people do on the models, the more they understand the process, the faster they actually develop a better technology. And so you can start from very early R&D stage, and that would actually help. The earlier you start, the better. So I think, yeah, that my preference would be to start quite early.
Great, amazing. And can AM Learn continue improving optimization models as more experiments are performed, or does the model require periodic retraining?
So as IAM's technology matures, of course, there will be some variations on the core technology, which means that the physical model may need to be enhanced, because there is better understanding of the underlying phenomena. But there is also more and more operational data being collected in-house, which means that the statistical models are becoming better. And so the company should be able to use those both statistical models and physical models, even for the tasks like predicting the behavior and architecture of the plant for new problems. So I would envisage that the company would be able to run the simulations before they run experiments when the new customer comes in and say, and actually already have some basic idea what they should do in the lab, so that it will help them to reduce the lab effort and reduce the costs in R&D quite significantly.
And how can a domain user explore the knowledge graph to ensure it is not a black box and understand the bottom-up approach?
So this is really shown in these diagrams. So when the user is assembling the models from phenomena, they actually see the equation. So here they see how the kinetics is being written, how the mass transfer is being described, how the sort of solid liquid mass transfer, gas liquid mass transfer. So then the user can even add custom equations. So here it says formula specifically defined. That is actually a custom defined equation for the solid dissolution, which is not in a knowledge graph. We didn't know about this before, but the user can add this knowledge. And it stays then in a knowledge graph that this is possible to describe this phenomena this way. So this is fully interactive, and the users can look at it and say, well, actually, I don't like this equation. I want a more detailed equation, and either ask the system to find another equation or propose a different model here. So it is fully interpretable.
And for researchers who are unfamiliar with AI or machine learning, how accessible is AM Learn today?
I think AM Learn is there's one picture where I have AM Learn shown. It's sort of here. So AM Learn is a no coding environment. So you don't need to have coding skills to work with this. People who want to know a little bit more, actually, there are some users who want to use their own algorithms and use AM Learn to do the equipment orchestration. So there is an API for advanced users, but for users who don't want to code, you don't need to. It's the environment is a user interface.
And the last question for today, does this digital twin require cloud storage to run, or it can be run on local systems or servers?
So this will very much depend on what an organization IT security is. So many organizations have local clouds, so you don't need to be on the public cloud. We used Azure or Microsoft simply because many organizations know what it is. It's not we don't have particular affiliation to this or anything else. We could choose anything else. We could choose Amazon, we could choose Big Blue, doesn't really matter. So if a company has a local cloud, which is not connected to the internet or the open public internet, that's more secure. However, you can make it also reasonably secure with the large cloud providers such as Azure or AWS. That those tools exist, and it's a internal choice of an organization.
Great, thank you. That's all the time we have for today. A quick reminder that this webinar is part of our ongoing AIM Academy series, where we share knowledge and tools to help accelerate materials innovation. You can explore more webinars, articles, and technical resources at acceleratedmaterials.co/AIM Academy. Thanks again for spending your time with us. We really appreciate it. Have a great day, and we hope to see you at the next AIM Academy session.